Ready.
Yeah, next up, we are excited to have Sangmei talking about the tap-free energy.
Yeah, it's my pleasure to talk at Simmons, and this talk is about the local convexity of tap energy and AMP convergence for a prototypical model for Bayesian inference in high dimension. And the result talk just talk about while the initial search phase is hard, while I would like to talk about while the final search phase is simple. And this is a joint work with Michael Salatano and Zhou Fan, and it's based on prior work with Zhou Fan and Anjam Hanari. Okay, so the motivation is to do variational Bayesian inference. And while there are 2 points of view in terms of variational inference, one point of view is optimizing a variational free energy, and another point of view is to use iterative algorithms. Variational free energy, for example, the variational Bayes, beta free energy, or the tap free energy. Iterative algorithms include leaf propagation, expectation propagation, message passing, and approximate message passing. Okay, so this method has been established for more than 20 years, have been written into softwares and works well in practice when people actually do Bayesian inference. The theoretical challenge are that, well, can they show that the minimizer of the free energy really approximates the Bayes posterior mean? And well, is the landscape of the free energy very good, and whether iterative algorithms converge? Okay, so in this talk, I would like to talk about a specific high-dimensional statistical model, which is the Z2-Synchronization in the weak signal regime. Okay, and we believe that while the whole story can be moved to other statistical models like generalized linear models or like spec matrix models. But here, today, we are focusing on the Z2 synchronization problem, and we are going to look at the landscape of the tap energy, and we are going to look at whether iterative algorithms will converge. Okay, so what is Z2 synchronization? Well, we have a signal x in n dimension, where each coordinate is uniformly +1, -1. Okay, so this is the prior of the signal, and we observe a noisy pairwise product of xi and xj. Observe this yij. The noise is assumed to be Gaussian, and while lambda is the signal to noise ratio, is assumed to be fixed, and when dimension goes to infinity. So that means, well, there is not an estimator that can be consistent. Okay, so you cannot have fully recover this x. You can only estimate this x up to a constant error as n goes to infinity. In matrix notation, we have matrix y, n by n matrix, which is a noisy GOE perturbation of the spike. Okay, so the task is to estimate this x given y, and because of the degeneracy of the Z2, well, perhaps we can say that we estimate this matrix, which is XX transpose. Okay, so, well, yeah, so this is a setting, and perhaps we can look at square laws. It doesn't matter. I mean, perhaps, well, let's say we look at square laws and, well, look at what is the best estimator. What does the best estimator can do? For lambda less than 1, this is information theoretically impossible. This is established results. And for lambda greater than 1, estimation can be possible and efficient. We can use just special estimator. And this is called the p-phase transition. And well, but the optimal estimator, the Bayes estimate, is a Bayes estimator, which is the posterior expectation of XX transpose given y. Okay, so here there is a plot of the limiting MSE achieved by the Bayes estimator, which is the posterior expectation of XX transpose, and the PCA estimator, which is a spectral estimator. And you can see that, well, the blue line is the Bayes. It achieves smaller mean squared error, and the PC estimator. And the threshold, both of them is at 1. Okay, so while the Bayes estimator is very good, and while people have shown good properties for this Bayes estimator, but the problem is, the question today we'll have to ask is how to compute this Bayes estimator. Well, definitely it's a high-dimensional integration problem. So we want to approximate it instead of compute it exactly. And what people do is variational inference. Well, there are 2 points of view: variational free energy and iterative algorithm. And well, the type free energy is the correct free energy to think about this problem. And while there is this approximate message passing algorithm, which are also standard in the literature. So in this talk, I would like to analyze these 2 objects. What's the type free energy? Okay, so well, the variational free energy point of view is that we want to find a function maps from the solid cube to a real number such that the minimizer of this function, we call it m hat, it corresponds to the Bayes estimator. So m hat transpose, well, should be the Bayes estimator. This is a function we hope to find. And the mean field variational Bayes, this is a naive free energy people use in practice, which is just which can be derived from the KL minimization principle. It's just a summation of entropy term and an energy term. But this variational Bayes free energy will not be the correct free energy in the sense that, well, the minimizer will not correspond to the posterior mean. So then, well, there is another free energy called the TAP, the tap free energy. TAP means, well, there are 3 physicists, Tollers, Anderson, and Palmer. When they look at spin glass, the SK model, they derived a free energy like this. Okay, so the difference between the TAP, the tap free energy, and the variational Bayes is that there is an additional Einstein correction term. With this term, while physicists conjecture that the minimizer of this type free energy will correspond to the correct posterior mean. Okay, so well, still this is in some sense is a conjecture, and we would like to understand, well, whether the minimizer of the type free energy gives the posterior mean, and also we want to understand the landscape of this type free energy. So one property is that this is a non-convex objective function, and there will be bad local minimizers. Well, the question is whether it has a nice landscape and whether the global minimizer corresponds to this posterior mean. So this is the first question we would like to ask. Okay, another question we would like to ask is about this approximate message passing algorithm. Well, it has a long history, and the AMP algorithm of this problem is just given by this iterative equation. The interesting, okay, so the important thing is that the k+1's iteration depends on the k's iteration and the k-1's iteration. Okay, another basic property of this AMP iteration is that the fixed point of AMP corresponds to the stationary point of type free energy. So this is just by trivial algebra. And well, another property is that, well, this AMP is not a descent algorithm on the type free energy. Okay, so it's not like gradient descent on the type free energy. It's doing something, some other things. But well, there are good properties of this AMP in the sense that people can show that the following property. Okay, so people can show the convergence of AMP starting from spectral initialization in the sense that, well, if we look at a fixed k and look at the k's iteration of AMP, compute the distance between MK transpose minus, okay, so Bayes estimator. Forbidden norms, okay, so this is a error. And first we take n goes to infinity, we can get a number epsilon k, we can fully characterize this number. And then as k goes to infinity, this number goes to 0, okay? So this convergence is not in the sense that, well, if you have a fixed sample size n, you have a fixed instance, you run AMP, it converts to some point that corresponds to the Bayes estimator. And, but it's a little bit different. You first take sample size go to infinity, and then you take k goes to infinity. Okay, so this characterization allow to characterize, extract a lot of information of the Bayes estimator. So it's a very good result. But in terms of optimization, it's still not clear whether if you run AMP for forever, whether if you converge to some fixed point. So people try to analyze, okay, so this result is established using state evolution analysis, which is standard, currently it's a standard tool to deal with AMP. And people try to improve the concentration from AMP to state evolution, but the state of art analysis only able to let k, the number of iteration, to be a little log n or log n. So this number of iteration is not enough to show the convergence of AMP. So the second question we're to ask is that, whether we can show the convergence of AMP algorithm for a fixed instance as k goes to infinity. So these are the questions we would like to answer in this talk. And here is a numerical simulation. Basically says that, the conjecture is that, the landscape of the type energy is quite nice and AMP converge. So this blue curve is the residue of AMP versus the number of iteration. You can see that, it converges very well. And for different initialization, it all converges to the same point. And we have some other algorithms which also converge, and I will describe it later. Okay, so first, the main result was by Zofan, me, and Andrea 3 years ago. It characterized the global landscape of the type energy. So it says that, suppose we look at the critical points of the type energy below some threshold. Then, when the signal to noise ratio is large enough, but this lambda 0 doesn't depend on n. So it's still in the weak regime. I mean, it cannot fully recover the signal. But when lambda is greater than this threshold, we can show that. Okay, so for any critical point below a threshold is close to the Bayes estimator. Okay, so this result, there is a geometric plot of this result. Okay, it says that all the critical points below a threshold are close to the Bayes estimator. Okay, so this, so the landscape looks like this. There could be bad local minimizers above this threshold. But if you look at critical points below this threshold, all these are close to the Bayes estimator. By the way, the population minimizer is not at the Bayes estimator. The population minimizer may be somewhere else. Okay, so this is the result we showed 3 years ago. Okay, but we can in this result we cannot exclude bad local minimizers near the Bayes estimator. We can only show that if there is a critical point, all these critical points are close to the Bayes estimator. And this result is established using the Kalk-Rice formula, which I will describe it soon. Okay, so then we have this result. Just to exclude bad local minimizers near the Bayes estimator. I mean, we can show that there exists a unique local minimizer near this Bayes estimator. So this is by Michael, Zhou, and me. And we show that, when lambda is greater than 1, 1 is the information theoretical threshold of this problem. So we can show that with high probability, there exists a unique critical point and unique local minimizer. They're the same. M star of this type energy up to a +1 - sign because of the symmetry, such that, this estimator and this minimizer is close to the Bayes estimator. And this type energy is strongly convex in a small neighborhood. And this neighborhood is not so small. I mean, the size allow us to prove give some algorithmic guarantee. Okay. So, the geometric picture is like this. We show that, near the Bayes estimator, well, there is actually just a unique local minimizer. There's not so many local minimizers even in this neighborhood. Okay, so this is the result for the landscape of the type free energy. So you can imagine that, well, with this geometric result, well, there will be a polynomial time algorithm to find these unique local minimizers. Well, the first guess would be gradient descent, but well, actually gradient descent may not work very well, but well, we come up with this natural gradient descent. But well, first let's look at, well, the iterative algorithm. First is like this AMP algorithm. Well, you can write it in this form, and there is this natural gradient descent algorithm, which is gradient descent preconditioned by the feature information. And well, people also call it the Bregman gradient descent or mirror descent. There are many names of this algorithm. So basically, this algorithm is doing like gradient descent, but well, in a different geometry. Like, well, you are calculating the gradient of type free energy, but you update it in the mirror space. So, well, you can look at the difference of AMP and the natural gradient descent are very similar. The difference is just that, well, there is a step size in the natural gradient descent. If you take the step size eta equal to 1, well, this is even closer. And the only difference is that here, the time indices k minus 1 is corrected to be the time indices k. So that in NGD, the k plus 1's iteration only depends on the k's iteration, not the k minus 1's iteration. Okay, so I think, well, NGD is a more natural optimization algorithm if you don't know about this statistical model. If you're only in the optimization community, perhaps you prefer this NGD than the AMP algorithm for optimizing this type free energy. And the good thing about NGD is that it's descent on the type free energy. Okay, so well, first result, we can show that a hybrid algorithm will converge to a minimizer M star. The M star is the global minimizer of the type free energy. So the algorithm is that first we need to do spectral initialization. Well, this is unavoidable because of the symmetry. We need to run AMP for T steps. This T is constant but large so that it drives you to the local neighborhood. And then we continue to run natural gradient descent with step size eta. We show that when lambda is greater than the information theoretical threshold, while these iterates will converge to M star and minus M star. So this convergence is for a fixed instance and for a fixed sample size n. It's different from the convergence of AMP result analyzed using state evolution. Okay, so well, this is a hybrid algorithm. Okay, so we show that, well, if you do spectral initialization, run AMP, go to the local neighborhood, and then continue to run NGD, it will convert to this unique minimizer. And the convergence of NGD is purely due to the geometric property of this type free energy. It's due to the relative smoothness and relative strong convexity. And well, how about if we just run AMP or just run NGD themselves, but not run the hybrid algorithm? Perhaps this is people prefer to do. And we can show that, well, when lambda is greater than a threshold which is greater than 1, we can now drive down this threshold to 1. Then with high probability, either spectral initialized AMP or spectral initialized NGD convert to the minimizer M star. Okay, so I mean the proof of this is much easier than the proof when lambda is greater than 1.
Really, either. Like it could be that you know, for some instance, like for some instance AMP works, and then for some other instance NGD works.
These are two theorems. One theorem is that AMP will converge. Another theorem is NGD will converge.
So they both do.
Oh, both. Okay. Actually, it's both. Yeah.
Okay, cool.
Yeah,
Thank you.
Sorry.
No. I mean, it makes sense now. But okay,
yeah.
got it.
Okay. Sorry.
It's also colored that one.
Yeah.
Okay. Yeah. It's a little bit
In retrospect, it's a very foolish interpretation.
It's true. If you choose one randomly, it works with high probability.
That's so hard to show. Okay, so well, how about perhaps another question is like, suppose we want definitely just use AMP when lambda is greater than IT threshold, whether it will converge. What we can show is that when lambda is greater than 1, this M star is a symptotically stable fixed point of AMP, in the sense that there exists a small neighborhood near the global minimizer such that AMP initialized in this neighborhood will converge to M star. But the problem is that this delta may depend on n. We cannot make this quantitative delta. Okay, so an open problem is that can we show that spectral initialized AMP converge as long as the lambda is greater than the information theoretical threshold? This is what we don't know. Well, this is a conjecture to be true, but we don't know how to show it. Okay, so here we just want to show some universality results. So the theorem is based on that noise is Gaussian matrix, but we tried other noise matrix, and empirically the result is the same. Okay, so I would like to briefly talk about the proof. First, let me show the technical challenge. So the technical challenge is that there's no uniform convergence happening. Okay, so because the signal to noise ratio is not so large, if the signal to noise ratio is large enough, what will happen is that the empirical risk will uniform converge to the population risk. The first and second order derivative of the empirical risk will be close to the population risk supreme over the M. Okay, so this doesn't happen. So this is a difficulty. If this happens, then we can just look at the neighborhood of population risk, which is X, the true X, and then analyze this neighborhood. This is a deterministic neighborhood and very easy to show geometric property. But the difficulty is that, when signal to noise ratio is of order 1, the empirical risk minimizer will be far away from the population risk minimizer. And then the empirical risk minimizer will be at a random location. So it's hard to deal with this minimizer of the empirical risk. And then, you want to not only locate where is the empirical risk minimizer, but also talk about the local geometry around this empirical risk minimizer, which is not an easy task. Okay, so the technical tool we use, the first technical tool is the calculus formula. Okay, so the formula is that, suppose we want to count the number of critical points of a random function in some particular region, we can compute its expectation using this formula. So the technical difficulty of dealing with this formula is just to calculate the expectation of determinant of Hessian conditional gradient equal to 0. And in this paper, we have shown that there is an upper bound of the number of critical points and related to the function S star. Okay, we have an analytical formula for this S star. And by analyzing this S star, we can show that all local minimizers below some threshold are close to the global minimizer. Okay, so the global geometry can be analyzed using this calculus formula and give it an upper bound. And you can see that this doesn't exclude bad local minimizers, not bad, but this doesn't exclude the possibility that there are many local minimizers near the global minimizer. So another technical tool we use is the conditional Gaussian comparison inequality to exclude those local minimizers near the global minimizer. So we need to analyze the Gaussian process. Gaussian is because the noise is Gaussian. Okay, so we need to analyze the Hessian, the least eigenvalue of the Hessian, when this M is in the neighborhood of the M star and the quantitative neighborhood of M star, conditional on that, the type energy, the M star is a critical point of this type energy. And the good thing of this Gaussian process is that even if we conditioning on this conditioning on this constraint, this type energy is still a Gaussian process. The Hessian of the type energy is still a Gaussian process. is a finite rank spec GOE. Okay, so the Hessian condition on gradient equal to 0 is a finite rank spec GOE matrix. Okay, so using the Gaussian comparison inequality, the Slepian inequality, we are able to show a high probability lower bound for the rescaled Hessian, which is given by this variational formula. And we are able to show that this variational formula is greater than 0. Okay, so, well, that means type energy will be locally strongly convex near some M star. Okay, but okay, so showing this result has some technical challenges, and we need some smart idea to show this. And well, the first technical challenge is to control the empirical distribution of coordinate of this M star. To control this, we use again the Slepian plus characterize to give it a tight control. And then we need to analyze this variational formula to show that it's greater than 0. And well, handling this variational formula well takes some effort, and well, first need to handle the bulk and then show the spike doesn't affect the bulk. And yeah. And then there is another non-trivial thing, which is that, well, here this M star is at a random location. Okay, so this high probability lower bound is for a fixed M star. So you need to have a union bound over M star to be a critical point. Okay, so it's not like, well, you have through this you are done. You need to take a union bound over M star, which could be a critical point. And to do this, well, there is a non-trivial, very non-trivial argument. We need to have a clever argument to obtain a union bound over M star using the characterize formula again. Okay, so this is the technical difficulty of dealing with the landscape of the type energy. And then we have, well, how to show the convergence of natural gradient descent. Well, this is purely due to a geometric property. Well, because of the landscape we have shown for type energy, we can show the relative smoothness and relative strong convexity. And then the optimization, simple optimization argument, well, non-random argument will imply the convergence of natural gradient descent. Okay, and how about convergence of AMP? Well, the way to show it is first to write this AMP iteration into this form. Okay, so we stack MK plus 1 MK as a function of MK and MK minus 1, analyze the linearized AMP operator. But while this is a little bit different from what people did in the literature, people did is to linearize it in the uniformity point. And here we linearize it M star, which is, well, conceptually the global minimum. Conditional on this type energy is a critical point. And while we are able to analyze this AMP operator, okay, I think it's a non-trivial argument. We are able to show that when lambda is greater than 1, with high probability, the spectral norm of this AMP, the gradient of AMP operator, the Jacobian of AMP operator at M star is less than 1. So that this implies the asymptotic stability of AMP algorithm at M star. And when lambda greater than lambda 0 with high probability, we can show the operator norm bound of this Jacobian of AMP operator when M is in a neighborhood, in a quantitative neighborhood of M star, so that this will imply the global convergence of AMP algorithm. Okay, so this is what I could talk about today. So we have conclusion in the following. Type energy has no sparse local minimum below a threshold when lambda is greater than a big threshold. It's locally strongly convex near the Bayes estimator when lambda is greater than the IT threshold. A hybrid algorithm, spectral AMP and NGD algorithm will converge to M star. And well, when lambda is greater than lambda 0, well, both these algorithms will converge. And AMP is asymptotically stable at M star when lambda is greater than 1. One open question is like, can we show that AMP converge when lambda is greater than 1? Well, and we believe the proof strategy can be extended to other high dimensional statistics inference problems. This is all I've talked about today.
Any questions?
Well, hey, Sam, thanks so much for the great talk. I guess I'm thinking about sort of the models that we've seen, sort of maybe like sparse spikes and stuff along the lines of what we have heard in the workshop before. So can you maybe say a few words about how the geometry will change? So for example, if the spike is sparse, then do you expect the geometry around the maximizer to change, or do you think it'll change like along the initialization, and how would it change?
If if sparsity is still linear in n, then I would guess the geometry will be the same. It will be still the whole result can be carried through when the sparsity is linear in n.
But there is a hard phase, right?
Oh, okay. Yeah, there will be a hard phase, and well, I will guess that in the fixed point, when the state evolution has a stable fixed point, then for that fixed point there will be a unique minimizer of AMP fixed point, and that AMP fixed point is stable.
Sure.
I don't know about what happened for the unstable fixed point of state evolution.
Other questions? Okay, let's thank Song again. So now we have lunch and we'll be back at 1:30.